live.
Hi. So, how's it going, Nick?
Good. Just fixed some internet issues. But I also realized that my coffee's not here, which I may have to go
That's
up and
tragic.
get some. Yeah.
I see. So,
How are you?
I'm okay. You can go. I can tell everyone who's here what's going on today.
Okay.
Well, you're not gonna know, but that's fine.
It'll be a surprise. It's okay. At least I'll have the coffee.
That's all right. Yeah. Priorities. So what's happening today is usually Nick and I hop on this phone call maybe at least half an hour before we start the stream to set up the audio and just say hi and how's it been going and stuff like that. And today we didn't do that. So we actually just said hi right now. I mean, I've seen him for a minute before when we're just tuning in whether my audio is even here or not. But that's pretty much it. So I have no idea what has been going on in Nick's life since we streamed last, and he doesn't know what happened for me. So it's all like up in the air and very mysterious. Fact is, I requested this quick stream jump on get on fast thing, and maybe we're also gonna end earlier just because I'm pretty strapped with time right now. I gotta do some bureaucracy stuff really early in the morning tomorrow. The last couple of days have been a little stressful, which is also why we didn't stream last Thursday. Nick said he's going to put up a little note, but then ended up not happening. And that's exactly why I think that Nick is the way that he is. But
I can't wait to timestamp this video. Oh man.
Well, so quick learning session today. Last time we skipped because I had to do stuff, and I just thought, because I still have to do stuff, but I thought let's just do a quick cram style learning session anyways, because when you start skipping stuff, it just gets kind of like the thing to do. So let's not skip and instead just do
Martin's being a trooper right
stuff, right? I'm a trooper?
You're a trooper.
A trooper. Yeah. I suggested with essentially what I'm gonna have to learn next is that I stay in one country and don't have to keep moving around, which is very much in the works, and maybe something's gonna change tomorrow, but it's still up in the air, so we'll see. That's all I have to say. Any interesting news to share from your end?
So I didn't get coffee because it's not ready, but this is like a green juice that's like
really
healthy.
Does not look like coffee. Yeah.
No, yeah.
Okay.
But I went diving yesterday, and it rained 2 days before, and I should have known better, but the visibility was essentially this. This is what I was diving in.
And you put it in front of the camera just for the experience, the diving experience.
Yeah. You know what? That's actually dead on. That's exactly what I saw yesterday. So it was it started like this, and then you went in, and then it just got so much greener. And you go maybe 3 feet down, or no, maybe a little bit deeper. Maybe it was 5 feet, and it went from that green to just pitch black. There was zero light penetration, and I was with a friend, and there was a bit of current too. We both went down. We came right back up at the same time, and we're like, yep, it's not even worth it. We can't see anything. So that was, we spent 15 minutes getting all of our gear up. It's cold, the dry suits, all this weight, bringing the tanks down to the beach. And then yeah, we just called it. So
no, you could have done some ethereal meditation session in pitch black, floating in a womb type of thing in the darkness. The universe envelops you.
Yeah, that would have been
Not
fine if the current wasn't as strong as it was.
Yeah, right. Well, it's part of this type of things that you don't know where you're going to end up.
Right. You couldn't even like see how deep you were on your computer. Like you would have to bring it to like up to your face. So yeah, no, he went down. This is our last thing, and then we'll get back into it. He went down like maybe like 2 meters away from me, went down there, and then when we both got up, he was 2 meters on the other side of me because the current.
Oh, okay.
And it was within like 6 seconds of him going over. So yeah, no, I would love to do like this just meditation session in this like pea
Beautiful.
green soup, and then get up, an hour later and you're floating in the middle of the Atlantic Ocean. Probably not the smartest thing to do. The water was also very, it was pretty cold. It was 44 degrees Fahrenheit.
Good. Whatever that means. But
Whatever that means
you survived.
In real world units. Yes. It's cold.
It's cold.
All right. Anyway, so let's get into this. Let's get into
Let's do it. We are back to number 7, sizing and TTA.
I thought we finished this.
No, we didn't. We just went.
This is very misleading.
Halfway.
Title. I thought we finished.
Oh, what did you say? What did you put in there?
I put in.
You said like we finished
8.
it.
Thank you.
It's a lie. That's all. We just went up to test time augmentation.
Coffee delivery.
Wow.
Do you remember this?
Oh, I do. Is that from? I do remember it. Where did we get it in France?
We bought it. Yeah.
Yeah. An original French press, so to say.
Yes, French press from
certified origin.
I don't know if it's actually made in France.
Probably not.
But all the warnings are in French, so it makes it feel more authentic. Anyway.
Attention.
Sorry.
Le café serait être trop chaud. Or something.
Yeah.
Anyways, so test time augmentation is where we're at. We went like halfway on sizing and TTA. We actually went nowhere on TTA because TTA is where we stopped. If
Okay,
TTA
so
means that
this is
which I think it does.
So this is not titled correctly because I
Okay.
was a little bit eager. All right, so yeah, we could probably finish this in the time.
Yeah, I thought
we have then
that
today.
kind of like feels like a nice
Yeah. All right, let's do it.
nice lessy
Let's do it.
lesson. Okay, I have no idea whether we have to run anything beforehand. Looks like we do. So we need that learner. So I'm just gonna start running everything above to here. Run before. And then we can start reading. You want to take it away, DJ Nick?
Sure. All right, test time augmentation. We have been using random cropping as a way to get some useful data augmentation, which leads to better generalization.
Oh, wait, sorry. Should we do any sort of recap from the last thing? And, like recap what's the plan for today? Plan for today is really just going to the end of this lesson, but
yeah,
recap?
what was the sizing stuff that we did last time?
Okay, because I also don't know.
Okay, so it was a bit of normalization.
ImageNet, I remember that. They trained like some sort of little ImageNet that doesn't need everything.
I like how both of them, we were reading that, and it's called, the bigger one was still called ImageNet, and then the other one
but
is
without the
ImageNet.
TE.
Yeah.
It's a small one.
I asked Google this morning, I was like, hey, what's the British spelling of gray? I didn't remember if it was with an A or an E.
Mm-hmm.
And then Google's like, just talks about the words gray. And it's like, the word gray is, both words gray and gray are used to describe a color between white and black. And I'm like, this is not. And the Google Home was just kept saying the words and not the actual spelling.
Voice-wise. I see.
So it was a lot of like both gray and gray. Gray is used here while gray is used here. It's like,
yeah, that doesn't help much.
like, thank you.
Doesn't
This was
translate to audio.
the most useful response. All right, so ImageNet normalization, Progressive resizing. Okay. It's starting to come back
There
to
was
me.
this
Yes.
too. So we started with like smaller images, trained on that, and then made them bigger and bigger and bigger, I think. Probably not as often.
Yes.
Yeah. With the same, like using the same learner, but passing it a different data loaders, different data loaders.
Right.
So we
With
changed
the different
out the
size and the different number of
batch
images
size.
too. Right. The batch size and the size of the image.
So we did that, and there's something's running, but it's waiting for me somewhere, huh? What you waiting for?
Oh,
okay, it's just doing some training. Well,
do we need to train?
keep at it?
Yeah,
I think we need the learner later, further down. I don't know if we need all of the training that's going on in here, but whatever.
Yeah, whatever.
Okay, so we did the progressive resizing, and that's it. Huh. Oh, I think we spent a lot of time on scientific notation. All right, let's move on.
We did do that as well. Yeah. All right. So we've been using random cropping as a way to get some useful data augmentation, which leads to better generalization and results in a need for less training data. When we use random cropping, fast.ai will automatically use center cropping for the validation set. That is, it will select the largest square area it can in the center of the image without going past the image edges. This often can be problematic. For instance, in a multi-label dataset, sometimes there are small objects towards the edges of the image. These could be entirely cropped out by center cropping.
This is exactly the thing we ran into, or the stuff we discussed, like I think twice, when we did the planet dataset. Right, you have multi-label classification, and if you do just a crop, then it might just take out some parts of the aspects.
Yeah, this can be problematic. For example, in a multi-label data set, sometimes there are small objects towards the edge. Okay, I think I just read that. Even for problems such as our pet breed classification example, it's possible that some critical feature necessary for identifying the correct breed, such as the color of the nose, could be cropped out. One solution to this problem is to avoid random cropping entirely. Instead, we could simply squish or stretch the rectangular images to fit into a square space. Okay.
I think that's what we ended up doing, right?
That was random. That was part of like very early on that like augmentation, and that's why I remember a photo of regs where the ball ended up like splitting into two because it was kind of like squished and then one part kind of turned around or something. Anyway, but then we miss out on a very useful data augmentation, and we also make the image recognition more difficult for our model because it has to learn how to recognize squished and squeezed images rather than just correctly proportioned images. Another solution is to not just center crop for validation, but instead to select a number of areas to crop from the original rectangular image, pass each of them through our model, and take the maximum or average of the predictions. In fact, we could do this just for different crops, but for different values across, for not just for different crops, but for different values across all of our test time augmentation parameters. This is known as test time augmentation, or TTA. Okay, so during inference or validation, it seems like the TLDR is during inference or validation, creating multiple versions of each image using data augmentation, and then taking the average or maximum of the predictions for each augmented version of the image.
So you run the prediction on all of them, and then you just select the ones. What it said. Select the average or the maximum predictions.
So you run a prediction on each variant or each version, and then you take the average. Okay, it's interesting.
Or whichever prediction came out the most amount of times. I guess you can decide whether you want to do average or maximum somewhere.
All right, depending on the dataset, test time augmentation can result in dramatic improvements in accuracy. It does not change the time required to train at all, but will increase the amount of time required for validation or inference by the number of test time augmented images requested. By default, fast.ai will use the unaugmented center crop image plus 4 randomly augmented images. You can pass any data loader to fast.ai's TTA method by default. It will use your validation set. Okay, so what do we have? We have predictions, targets, learn dot. Okay, it's got its own little function.
TTA. Learn.tta. So you call that, yeah. So instead of just doing learn.predict, which is what we usually did, where it just takes whatever the image is, I guess, that you pass in, then you do learn.tta.
Mm-hmm. And what is this accuracy? Accuracy prediction. I guess that's another built-in fast AI function, right?
I'm just, so what's the image that it's doing this on now? Because we're not passing anything to TTA. Right? Like what is...
TTA gives us a good boost in performance. Do we have, what is learn? Does
learn is our, it's the program that we're building up here.
But it says like learn has a validation set, right?
Yeah, I think because we split up in...
so I think that's what it was saying. It's using, by default, it was using the validation set. So it's probably using learn's validation set to do...
all of the images in the validation set? And that's like the average?
Or the item, average. Like, I don't know, maybe item just, does it select one?
Okay, and let's move on. Maybe it explains.
As we can see, using TTA gives us a good boost in performance, no additional training required. However, it does make inference slower. If you're averaging 5 images for inference, will be 5 times slower. We've seen examples of how data... Okay, so this doesn't really tell us anything about that.
It doesn't, yeah. Because, right, if we do predict, we always pass in an image that we want to predict for.
Mm-hmm.
And TTA must be, yeah, you're right. Like it says that by default, it uses the validation set. So images must be all of the images, and maybe then an average of all images. Sounds kind of weird. I mean, it sounds fine. It just sounds weird if it's not explained. And what's dot item?
Dot item feels like it's taking a random one. Like, I feel like fast AI has done that in the past.
Let's
with
see.
Stuff.
That's a dot item on what? On accuracy. I wonder what object we get when we call accuracy and predictions target. Fast AI accuracy object dot item. Metrics. Accuracy. Compute accuracy with target when prediction is PS times n classes. And that gives us what? What do you output accuracy? Error rate, accuracy, return an average. Okay, so compute accuracy with target when prediction is prediction target, return prediction equals target. So that's going to be what? That's going to be a Boolean. I'm confused. So it's taking a Boolean and then it's making a float and then the mean. Do you know this about Python? I don't think that's what's happening here, but let me show you something, just because it's fun. And a useless detour. So, what would you think that this makes, Nick?
True plus true.
Or let's say a more interesting one, maybe.
False minus false plus true. So there has to be some sort of like default value for false, right? Like it's either 0 or 1. That's my guess.
Does it have to be?
That's my guess. So if you did false minus false and it was okay, in this case, my theory that there's a default value false, let's say, I'm just guessing, is 0 and true is 1. So 0 minus 0 plus 1 would equal 1.
Yeah, correct.
Oh, okay.
It's funny though, because you can do like, so it's interesting. I don't know. It's not really something I knew, that if you do false just like that, it's false, right? Or true. But you can do true plus true is 2.
Yeah.
Because Boolean values in Python are actually like a subclass of integers, which is kind of weird.
Oh, interesting.
But interesting to know. So, which is funny because you can do things like this. Oops. P, right? And then you can say which is totally messed up. Or
man. It's you know, these are like, I feel like these are the nuances of like certain languages that like the language developer maybe didn't, or like, I don't know if they considered as like what they would use it for. Sure. But then you have people who like find this stuff out, and then you get like messy code, and you're just like, or right, like it's like,
I mean, you really
people
should
trying
not
to be
use
too
this,
clever.
You know,
yeah,
this has nothing to do with being clever.
Well, but I think there's a point here, right? Because like, I mean, how would you use this in a like real world scenario, right? Like if you had a list of different values, or like A, B, C, D, blah blah blah, and then you wanted to know, I don't know, if a certain case equaled true this many times, then you would like return back maybe like a list of names. So, well, all right, let's do this.
Yes,
let's say,
what does that have to do with this?
Well, hold on. If you had, no, it wouldn't work. Never mind. I'm just saying, I feel like there's like, you can probably find code like this online, and people think that they're being very clever, but I feel like it's poor practice and form.
I think
and it's like you're trying to be clever, and like, yeah, it works, and you did it in a way that like is not, you know, what you would normally see, but it's making the code much more difficult
totally
to understand.
Obfuscates it.
Yeah.
That would work. Ta-da! Okay, useless detour aside.
There's something similar in Go. Like they all have, there is like this default value for integers, for these different values. So like every data type has like the default value.
So why I came up with this in the first place is because here it seems to do a comparison, you know, equals is comparison operator. So, and the result of a comparison is either true or false. So this is going to be, if prediction and target are the same numbers, which I assume they're going to be numbers, then it's going to be true, and not otherwise it's going to be false. And then it's making a float out of that. So you see, like, this is going to have to, I mean, maybe, I don't know, maybe this dot float does something else, you know, because that's not the default Python one. That's something they built.
Okay, I could see. All right, so like it would take a 0 or a 1 and turn it to like 0.0 or like 1.0, right?
But there's no point in that, and then take the mean out of it, you know.
Yeah.
Right. So I think this dot float is probably a method that they built on top of some custom integer object or Boolean objects. You know, maybe they did something so that if you compare internally, that if you compare these types of objects, they're maybe not integers, but maybe some sort of fast integers that have their equal method written in a way so that it outputs something else than just true or false.
So you
I don't
can
know why
actually
you would
do that
do that
too. You can have you can make that comparison operator do something else.
Yeah. In Python, like all that these things are, like if you make a new class, data, you can define this with the dunder. I think it's eq.
Interesting.
Right.
So that means that now this comparison operator does something totally different.
Yeah, right.
Or
I could say
potentially.
always return 42 if I do this. So now I can make a date. I can say I make this one item and then another one. Or I could compare it to anything, I guess. I think it's the second thing that I compare it to. Definitely if I make two of them. So I can say and then I can say D equals E. And probably because I have to do a self and other. Might be. I'm giving it 2, yeah, so probably, let me try that again. Crap, I messed it up. Okay, once more. So, because it needs to take in a second object. And that it does that by default. Okay, so let's try again. Now if I can make these two objects again and then compare them, I should output
so
as
much faster.
42. Yeah, there you go.
So,
oh yeah, they might have just overwritten this equals operator so that it does something else than the default.
Wow. Huh. I didn't know you could do that.
Because otherwise it doesn't really make any sense in here. Otherwise it would always be 1.0 or 0.0 and then this mean is probably also something they did.
And is this this is something that you typically see, like people overriding these functions? Like, is this good? I mean, it's in fast.ai and one can assume, it's like a production library, like you would assume good practices, but like, is there a reason why it's not like they just did like a dot equals and then pass in target, like pred dot equals pass in target and then do the float, and
it just makes
more
it kind of like
readable.
natural to write. It depends. Yeah.
Well, like I guess like in what I'm suggesting, it would prove your theory, like it's obvious.
Yeah.
This is a bit more, you have to do some digging.
Because you don't know what these things are, right? They could be, if they could just be integers, then it's confusing if they're not custom objects. And yeah, you're right that like this dot float is more obvious because it's a method on top of whatever this object is that this returns.
Mm-hmm.
So it's a bit more obvious that they built something specifically. It's true, yeah. Might be nicer not to do that.
Wow.
Interesting.
Yeah, very interesting.
But yeah, generally you can do this for all of these methods. For the addition, all the operators are just some dunder methods under the hood.
Do you want to quickly just re-explain that for Jonah Vision, why the double equals is overwritten?
So I'm not sure why they did it, but I assume they did it because it's just a quick way to write it, like
just to I guess like the reason why we think it's overwritten is because if it's not, we don't know what that dot mean is. That was really the thing that kind of threw the wrench in the whole thing. Because if it's two booleans and it's a 1 and you turn it to a float, okay, you could see that. Or a 0 and you turn to a float, fine, you could do something with it. But like, why is there a dot mean? You're taking the mean of a float, of a single float. Feels weird.
And even like, if this would really be the normal double equals operator in Python, and those would actually be normal integers or floats, I don't think it would make any sense already here, because it's either going to be 1 or 0 then through the weird fact that true and false are integers, like subclasses of integers in Python. So it would always just be 1 or 0. Like everything else would get lost in here. So I don't think that makes any sense.
But
see what I'm saying?
We're not like mathematicians, or like, it took us 20 minutes to understand scientific notation in the last stream. So like maybe there's a reason. I'm just gonna throw that one out there. But I think at a glance, to answer that question, that dot mean put us in that little rabbit hole of Martin then explaining to me how double equals could be overwritten, because I didn't know that you could do that in Python.
That's all. But it doesn't really help us anything.
Yeah, we're just kind of stalling because our model is still like training from the last stream. We can't really move forward. I mean, we can,
We
but
can. We're just reading
we're
anyways.
just reading.
Where is it at actually? What you doing? Are you stuck somewhere? I did check. It's running on GPU. So just saying. Wow, it's still very high. You're still
Whoa, hold on. Is that 17
saying
more
6
minutes?
minutes.
Do we need that one?
Arn. No, we don't.
Yeah, let's close that one out, and I think we
Wait,
could.
and then wait, let me see. Is that true? X, Y. Yeah, I don't think we need that. I think we just need this one.
No, wait, hold on. Arn is go back up. I think we it's not really Arn. It's learn.
Ah.
I did that last time too. Yeah. So Jonah is saying you're taking the mean over an array. Like if you make 2 NP arrays of 5 numbers each, then try that function. So
wait, you're saying that's what's happening in here?
The predictions equals target, that is returning back an array. Each array of zeros and ones.
Because it's all the predictions over the whole validation set, maybe. So one prediction for each image in the validation set.
Pretty sure it's taking an image. Okay, across 5 numbers.
Mean across the 5. The mean across the 5 numbers. What's that supposed to mean?
Like it's getting the mean over the array. The mean of the array. So predictions equals target.
Wait, so how do you interpret this, Jonah Vision? That the predictions equals target, assuming now that these are arrays of numbers, right? Like an array of predictions and an array of targets, what it's supposed to be. And then, yeah. No, I think you're doing good guesses.
Yeah.
That's a bit harder for me to try because I don't have any numpy around. And this stuff is still running. Anyways, I can just go in the best place on the world, my desktop. Is it worth it to try that out? I mean, we're kind of like waiting for this.
Yeah.
So wait, so but are we running something unnecessarily? Because this is going to do 5 cycles. And then we have another learner down there. Do we need both of them?
I don't know that we need.
You see?
Yeah,
There's
I don't think
one.
we need. If we're going to do it again, like we should just run one of them. Right? Or
right,
let's scroll down and look at what the TTA stuff is. Are we training
that's even another one. Look, so I guess this is this progressive resizing, right? Where we started off with the smaller one, and then we're comparing the results of those.
But do we need that in the TTA section? Like, do we just end up
we're
training
doing something
another?
we're doing something with learn. You see? Like we're calling this TTA.
Scroll down a bit.
Method on it.
Because that's like maybe we could just assume that that's the answer or whatever. And what else are we running? Okay, we have some math, papers in math.
And sidebar. I don't think this has anything to do with the other stuff.
Nothing to, yeah.
Yeah.
So scroll down a bit. What else?
Oh, maybe this is all related.
Oh, there's learn.
And there we're running it again.
That's not. Is that a?
That's
code
not
cell?
related. Yeah.
Is that just markdown?
Oh, you're right. It's not a code cell.
Yeah.
It's just theoretic.
Scroll down. Scroll down. Yeah, it seems like we're not going to be running it. Anything.
We're just reading, huh?
We're just reading today. Yeah, those aren't.
Oh, that's fun.
Yeah. I think so Jonah Vision saying predictions and targets, and he put a few like those two arrays there. But
And then
I think
just compare them.
I saw something when we were scrolling down too that may make it a bit more clear.
Okay. What's that NumPy arrays?
Hold on, just go into the Colab.
Sure, I'm just doing this on the side.
Yeah.
Because
right
I'm such a
right there. Is that
multitasker.
Would that not be it right there? Those two arrays, 0, 1, 0, 0, 0, and
I mean, they're doing and, they're not equals comparing them.
I know, but I think they're saying that one is the predictions, one's the targets, and then there's the final result.
Okay, the third image is built by adding. Okay, sorry, I was reading silently. In this example, should the model predict church or gas station? Here. The right answer is 30% church and 70% gas station, since that's what we'll get if we take the linear combination of the one hot encoded targets. For instance, suppose we have 10 classes and church is represented by the index 2 and gas station is represented by the index 7. The one hot encoded representations are Roop and Roop. This is church and this is gas station. Index 2, yeah, church is index 2, 0, 1, 2, and this is 7. So our final target is, because you combine the 1 with the 0, you get 0.3, and then...
Yeah, I don't know that one. Anyway, I just saw those two things really quickly, and if it has nothing to do with it, we could go back into the...
I mean, I kind of want to try this
real go
quick,
for it.
if you don't mind.
No, not at all. We're just reading today. This is the fun stuff.
And then, okay, let's do A equals mp.array, and then I think we just pass in something like that, right? Okay, I'm gonna take your suggestions, Vision predictions, and we're gonna say 0, 1, 0. Look at me copying. Oh, I made a mistake actually. 0, 1, 0, 0, 1. There you go. Okay.
And then targets are all ones.
Okay. Targets. Oops. Targets. Okay. And
I'm impressed right now. I didn't know that you were this proficient in.
And this is very. Do you say I made a ton of mistakes here?
I don't even
using
know
it as
how
a little
to
chance
exit.
to practice.
I don't even. I shut down my computer when I have to exit a Vim
Not true.
shell. Take the battery out.
The battery out. So what does that do for us? Nothing. False. Okay, so it gives back an array where that points to where they're the same and where they're not. True, false. And then they're taking the mean of such a response. So maybe that's going to be a NumPy array, and then dot float dot mean. Maybe those are actually NumPy functions. Just see whether we were talking. We weren't talking bad about them. No, okay, so it doesn't have that. So this arrays the dot float, maybe that's something then that they implemented. Seems at least that the array that it produces with the true and false inside doesn't actually have a dot float method, maybe dot mean. Oops. It does have a dot mean. Interesting. Well, look at that, Nick.
Mm-hmm.
That's actually pretty close already to something that makes sense. Still not sure what this dot float does, but it probably just applies a float. Well, but if this is true and false, then again, it's kind of confusing.
So this prediction equals target is returning back where they both equal the same. It's creating a new array where each
like that.
Yeah.
Each compared thing is either
the
true
same,
or false.
it'll return the same.
It'll return true, and where it's not the same, it'll return false.
Right. Okay.
And then it seems you can take an average of those things, which, so if this is 0, 1, 0, 0, 1, so we have 1, 2, 3, 4, 5 of them.
That's true.
Okay.
That's accurate.
Interesting. Okay, so what we should be getting back here probably, I mean, this dot float, I assume it just does something to make sure that it's a float.
Maybe try tensors instead for NumPy.
Does NumPy has tensors? Like npa.tensor or what? Is that a thing?
I don't know.
Oops. I don't know either.
I really wish I had faster internet that I can like do something other than just sit here and be useful.
Man, you love it.
I really do. I'm like, I want to like either get faster internet or like after we're done with fast AI and we're like building stuff, something where I can interact a bit more and I don't have to yell at you to control your screen.
So let's then try this also. Oops. Are you enjoying this, Nick?
I
know you just said that you don't. Tensor has no attribute tensor.
Tensor was a fast AI thing, no?
Yeah, no.
Or PyTorch. Yeah.
Yeah, PyTorch. Yeah. Okay. No. I'm just gonna do an executive decision here. I don't want to go further down this rabbit hole.
Come on.
But yeah,
let's do PyTorch.
I don't even have PyTorch, and I gotta install it.
Okay. All right.
Wow, I'm quickly swayed. So then I'm gonna have to import PyTorch and do PyTorch.tensor. People.
Well, in the meantime, we're on Mixup.
Are we? No, we were somewhere here.
No,
we were like,
that.
Oh no,
we realized it wasn't anything. Yeah.
Okay, Martin reads Mixup. Oh no, you, Nick, go ahead. I've just been typing so much. I'm gonna hold my fingers up and eat a bite of an Austrian Kapfen sitting around here.
That looks so good.
It's just a donut without a hole and some jam inside instead.
I know, but that looks, I don't know. It just looks good.
Read.
Cheers. All right, Mixup. Introduced in a 2017 paper, Mixup Beyond Empirical Risk Minimization by Hongyi Zhang. Ongyi, I think that's how Ongyi Zhang et al. What is et al again? It was like
there's other authors as well. So it means it's not the only author. It's just the main author, and then there's other ones.
Very powerful data augmentation technique that can provide dramatically higher accuracy, especially when you don't have much data and don't have a pre-trained model that was trained on data similar to your data set. The paper explains while data augmentation consistently leads to improved generalization, the procedure is dataset dependent and thus requires the use of expert knowledge. For instance, if it's common to flip images as part of data augmentation, but should you flip only horizontally or also vertically? The answer is that it depends on your data set. In addition, if flipping, for instance, doesn't provide enough data augmentation for you, you can't flip more. It's helpful to have data augmentation techniques where you can dial up or dial down the amount of change to see what works best for you. Okay. Mixup works as follows for each image. Select another image from your data set at random, pick a weight at random, take a weighted average using the weight from step 2 of the selected image with your image. This will be your independent variable. Take the weighted average with the same weight of the image's label with your image's labels. This will be your dependent variable. In pseudocode, we're doing this where t is the weight for our weighted average. So image 1, image 2, data set, random int. Okay. Where t is our weighted average.
So I kind of like zoned out here. This was a bit too much of the same words.
Take a weighted average using the weight from step 2. Okay, so we're picking a random weight. Pick a weight at random.
So like another image from your data set. Okay.
Take a weighted average of the selected image with your image.
Okay, so you start with one image, then you get another image. So I have one image, I take a second image, then I take a random weight, then I do the weighted average
of the selected
with this
image
random weight
of the first image with the
of
other.
The selected,
I guess, right?
Of these two combined.
Okay, and
that's my independent variable.
And then take a weighted average with the same weight. Okay, so the initial random weight of this
image's
labels with your image's labels. I don't understand of this image with your image.
You're just like putting the image that you're interested in and a random image, you're putting them together. And then this part is about getting the data of the image, like the number, the pixel values. And this is about getting the label
So the
values.
image that you're trying to predict against a random image from a data set.
Yeah.
Okay.
I'm not entirely sure.
Yeah. Okay. Image to target. So image versus target. I guess.
Image 1 plus. So T. What is T? T is the random weight.
Is the weight for your for our weighted average.
So we have an image somewhere, image 1. Then we're getting a image. So that's the X values, all the image values. The target is the labels. We're getting a random one from the data set. We're getting a random weight between 0, 5, and 1. And then we're making a new image that... So okay, this is what this is about. Right? This is the image we're interested in. This is a new randomly picked image. We're creating a new image that consists of both of those images.
I don't know, maybe.
Yeah, look, because we're making a new image with a new target, and it consists of the data of both images. That's this part, with the random weight thrown in, and the labels of these two images with the random weight thrown in.
Okay. Maybe it'll clear up. Okay. For this to work, our targets need to be one hot encoded. The paper describes this using the equation shown in the open close bracket, where lambda is the same as t in our pseudocode. Contribution modified by this. We introduce a simple data agnostic data augmentation routine termed Mixup. This looks like it's from that paper, no?
Yeah, I think it's a snapshot from the paper.
And it looks like it's the same. They're just putting it in
that's what they're saying, yeah. In mathematics. They're just putting it into harder to understand notation. For me.
Sidebar, papers and math. All right, we're going to be looking at more and more research papers from here on in the book. Now that you have the basic jargon, you might be surprised to discover how much of them you can understand with a little practice. One issue you'll notice is that Greek letters such as lambda appear in most papers. It's a very good idea to learn the names of all the Greek letters, since otherwise it's very hard to read the papers to yourself and remember them and remember them, or to read code based on them, since the code often uses the names of the Greek letters spelled out, such as lambda. Okay, the bigger issue. Good thing you have a Greek guy on the podcast.
On the team.
There you go. A podcast, a stream. Oh man. The bigger issue with papers is that they use math instead of code to explain what's going on. If you don't have much of a math background, this will likely be intimidating and confusing at first. But remember, what is being shown in math is something that will be implemented in code. It's just another way of talking about the same thing. After reading a few papers, you'll pick up more and more of the notation. If you don't know what a symbol is, try looking it up on Wikipedia's list of mathematical symbols, or drawing it in Detexify, which using machine learning will find the name of your hand-drawn symbol. Then you can search online for the name. Yep.
Okay.
Okay. Lambda
Seriously?
is one of them. Pitchfork.
Pitchfork.
What is that? Par?
Wait, should I do it again? Now it looks like a. Oh no, look,
Lambda's still there. Yeah.
For me, now it looks like a dynamic, like a stick figure that's doing some stretching. The head's out of the window.
Yeah.
Window.
Oh, interesting. I thought that was the leg, and they had their hands down. It was like a downward dog, but the leg was up.
I see. I can show you the pitchfork again if you're interested, what it gives you there. Pitchfork.
Now do a pitchfork the other way. There you go.
Sigh.
Psi.
Psi. Psi. Oopsie.
Oopsie. And now connect the two. So like do kind of like a loop, like a U, and then then go down towards the middle.
Like that?
Yeah, but you want to connect, like make it like one continuous line.
Ah, okay, I see.
There you go.
Phi. Is that? Phi?
Mm-hmm.
Varfi. Varfi. Okay, interesting.
You know, it's funny. It got smiley before you even finished. Smiley.
It did?
Yeah.
Okay. Fine.
Pretty cool.
All right, sweet. That's fun. And sidebar. End it. Okay, so we got some code here that shows what it looks like when we take.
Do you want to go back into let's go back into the PyTorch. You do some work now.
How do you like that? Set up install for PyTorch. Error. What's your problem?
Error. I mean, you should just consider updating. Such a
still worked.
Passive like suggestion.
Oh, but that's just the.
It's just a funny structure.
Okay, so the suggestion was pytorch.tensor.
Torch.tensor.
Oh.
Well. I mean,
Torch
but
tensor?
if you're doing, I guess, import PyTorch. I don't know.
That's how I import it, I assume, right?
I don't know. Let's run it.
See. Yeah, it looks like the the error wasn't just pretending to be an error.
Mm-hmm.
Okay. Oh, helpful error messages. I tried to install PyTorch. The package name for PyTorch is Torch.
Like at that point, why doesn't it just say like, do you want to download Torch? Yes, no. Like we clearly found.
I could.
you know, like pip, step your game up.
Yeah, but I mean, I prefer this than it just downloads whatever malicious package someone put under the name of PyTorch up on PyPI.
Well, that's what I'm saying. Like this is getting
So
like returned, right? The exception. It says you're trying to download PyTorch, but the package named for PyTorch is Torch. The next line I think should be, do you want to download Torch? Do you want to download this PyTorch as Torch? And then just changes the name, right? And downloads the correct one. I don't know. Just a suggestion.
What? And do you include some sort of text that you can?
Right, literally right there. Like after that
output?
Well, no, like I'm sure you've seen it in like other CLIs where it's like you just type in Y or N and then hit enter and it does it.
Okay. Yeah, I could.
And then if you're like no, then it just returns the rest of it, gives you that nice little warning, tells you that you're behind, and then exits it.
Because I'm not even that behind, let's be honest. You're using pip version 21.1, 23.3. Come on. It's yellow.
Is it double?
I get it.
Double, what? I wonder what pip version.
We're all friends here. Generation's suggestion I should just run it in Colab in a different window, which is an option. I was just kind of hoping this is going to be quicker, but it really isn't, huh? Especially because we didn't end anything. We're still just hoping it's miraculously going to speed up and do all our training really fast. Because now it's on the second one, I think. Which, is this already progressive resizing or still not? No, it's not. So it's going to train still 2 more times.
Yeah, but we're not really running it.
I've kind of given up on it. Yeah. I just let it run.
Well,
okay, so blah, blah, blah. So this is what it looks like if you take a linear combination of images as done in Mixup. Church, make an image, pick it out of here. Okay.
I'm also on 20.2.2. I think I just updated
comparing
it,
pip versions.
That's all I can do. I can't go online and touch anything else. And even comparing pip versions, on Streamlabs,
but you could have
OBS, it's like complaining because I'm using too much CPU.
So Nick, you could have totally done all this stuff that I'm doing here on the CLI, right? There's no need for more internet speed. I could have given you power to share your screen.
That's the thing. I don't know that it can handle me sharing my screen plus a video to send to you and then also stream all of that. I don't know.
I don't know either.
I wonder if I could change. Can I change my quality
in something
to you?
Okay. So, Journal Vision, this is what we get when we try it with a tensor. Runtime error can only calculate the mean of floating types. Got bool instead. Okay, so that's the first one, which is probably why they're doing the float on it before, which means that this is the one that's failing, and the other one probably works.
I think Martin probably has more. Martin's pip is probably bigger.
Damn.
He's got more packages installed for sure.
What?
Jonah Vision is asking whose pip is bigger.
Okay, so yeah, it's true. So this is all just PyTorch. They didn't do anything. So all that's going on in here is comparing two tensors, PyTorch tensors, to each other, getting another PyTorch tensor with true and false on as a result, then converting them all to float because this is the only way that it can call the mean on it.
Mm-hmm.
And it works like that. Wait, this is still so messy. Let me clean it up and then run again. So this is what we get. We get the tensor a tensor of booleans, then we convert each of the boolean into a floating point 0.0, 1.0, 0.0, 0.0, 1.0, and then take the mean out of that. Okay.
Why is there a double space in front of true? And a single space in front of false.
Tune in next time. When we
right, like that's not like you didn't do any of that. That's just how it's returning.
Yeah. Okay. So I think I kind of get the point of what's going on here. Like we're getting, right? Like we're doing this church. We're getting these two images, resizing them, converting all of the. So like here it's happening. It's converting all of the numbers in the tensor that makes up the church image into floats. That's a normalization. Okay, so divided by 255. So here we're doing normalization. Here we're doing another normalization. What's this dot about? It's just making it a float,
right?
Yeah.
It's just finishing the sentence.
So final. Yeah, right. I thought for a moment. I'm putting a period. Done. Okay, then it's drawing them. Show the image, and then make a third image that consists of the two images with 30% church and 70% gas station.
Mm-hmm.
The third image is built by adding 0.3 times the first one and 0.7 times the second. In this example, should the model predict church or gas station? The right answer is 30% church and 70% gas station, since that's what we'll get if we take the linear combination of the one-hot encoded targets. For instance, suppose we have 10 classes and church is represented by the index 2 and gas station is represented by the index 7. The one-hot encoded representations are So our final target is, okay. And so, so how is it getting to this one? 1 minus, no, so that's the percentages. That's the mean. Okay.
Isn't this what we were saying before? Like, those are all false. Or no, I don't know. I'm going to stop speaking and let you finish.
No, I'm finished. Yeah. Generation just said that also. I think we have some sort of a lag between the stream and the chat.
Oh, totally.
But yeah, we saw that too. That if you just do the mean directly without first converting it to float, then it errors. Wait, no, I'm actually, so how's it getting to this 0.3 and 7?
I think this is like what we were doing with the operator, like true false double equals thing, but the numbers don't really add up, where it's like, the only differences are the first one being that first classification, right? It's none of the other ones, and then the second image is that second or third to last.
But that can't be a mean, right? Because if we take a mean of this one and the mean of this one, it's going to be the same.
No. I don't think it's running the mean on this. It's just saying,
right, this
is the image, that's the image. It's going to run the classification and it's going to say it's 30% church, and then put that in this, because this is like the idea of like the one hot encoded thing, right?
Mm-hmm.
So like the final target is in the second position. It's 30%, and that's what it determined. It's 30% this category, and then it's 70% the other category, and then just put it in those places so that it can return that last thing, and then say it's
okay.
That's what I'm guessing.
Gotcha.
Because we saw something similar to this in the in like the other multi-label classification with the planet set, right?
Mm-hmm. Okay, so this is all done for us inside fast.ai by adding a callback to our learner. Callbacks are what is used inside fast.ai to inject custom behavior in the training loop. like a learning rate schedule or training in mixed precision. We'll be learning all about callbacks, including how to make your own in somewhere else, different universe. For now, all you need to know is that you use the CBS parameter to learner to pass callbacks, CBS. Here's how we train a model with Mixup. Model ResNet 50. Oh yeah, we're doing this huge ResNet also. That's why it's taking so long. Dataloaders.cbs.c. Learner data loader, model loss function, cross entropy loss, metrics accuracy, CBS. There it is. CBS Mixup. Callbacks. CBS callbacks. Fit one cycle. What happens when we train a model with data that's mixed up in this way? Clearly, it's going to be harder to train because it's harder to see what's in each image. The model has to predict 2 labels per image rather than just one, as well as figuring out how much each one is weighted. Overfitting seems less likely to be a problem. However, because we're not showing the same image in each epoch, but are instead showing a random combination of 2 images. Overfitting seems less likely to be a problem. However, because we're not showing the same image in each epoch, but are instead showing a random combination of 2 images. Mixup requires far more epochs to train to get better accuracy compared to other augmentation approaches we've seen. You can try training ImageNet with and without Mixup by using the examples train ImageNet.py script in the fast.ai repo. At the time of writing, the leaderboard in the ImageNet repo is showing that Mixup is used for all leading results for trainings of more than 80 epochs.
Wow.
And for fewer epochs, Mixup is not being used. This is in line with our experience of using Mixup too. Now we're back to the many epochs that this other guy was talking about earlier. Forgot what his name was.
Mellinger, I think.
Mellinger. It's using this, I think, show image. Training said something, but I don't understand what he means. Show image 0.3 times charge.
Plus.
Yeah, it's using, I mean, that's like some sort of this thing here, right?
Mm-hmm.
That's what he's talking about. Okay, I'm not sure. Maybe I misunderstood because I don't understand. So I probably misunderstood. Okay, 80 epochs. One of the reasons that Mixup is so exciting is that it can be applied to types of data other than photos. In fact, some people have even shown good results by using Mixup on activations inside their models, not just on inputs. This allows Mixup to be used for NLP and other data types as well. There's another subtle issue that Mixup deals with for us, which is that it's not actually possible with the models we've seen before for our loss to ever be perfect. The problem is that our labels are ones and zeros, but the outputs of softmax and sigmoid can never equal 1 or 0. This means training our models pushes our activations ever closer to those values, such that the more epochs we do, the more extreme our activations become. With Mixup, we no longer have that problem because our labels will only be exactly 1 or 0 if we happen to mix with another image of the same class. The rest of the time, our labels will be linear combinations, such as this 0.7 and 0.3 we got in the church and gas station example earlier. One issue with this, however, is that Mixup is accidentally making the labels bigger than 0 or smaller than 1. That is to say, we're not explicitly telling our model that we want to change the labels in this way. So if we want to make the labels closer to or further away from 0 and 1, we have to change the amount of Mixup, which also changes the amount of data augmentation, which might not be what we want. There is, however, a way to handle this more directly, which is to use label smoothing. Okay, we can do that.
Yeah.
Yeah, sure. Just gotta pack later on. And then next time I might be still here or I might be in a different country. Tomorrow is decision time.
What country?
Croatia.
Croatia?
Mm-hmm.
Okay. All right. Label smoothing. In the theoretical expression of loss in classification terms, our targets are one hot encoded. In practice, we tend to avoid doing this to save memory, but what we compute is the same loss as if we had used one hot encoding. That means the model is trained to return 0 for all categories but 1 for which it's trained to return 1. Even 0.99999 is not good enough. The model will get gradients and learn to predict activations with even higher confidence. This encourages overfitting. And gives you an inference time.
At inference time.
It's nice, right? Those two letters make such a difference.
It's just one letter. The two letters. Yeah, okay.
This encourages overfitting. I'm just skipping words. This encourages overfitting and gives you at inference time a model that is not going to give meaningful probabilities. It will always say 1 for the predicted category, even if it's not too sure, just because it was trained that way. This can become very harmful if your data is not properly labeled or perfectly labeled. My goodness. In the bear classifier, we studied in open close bracket. We saw that some of the images were mislabeled or contained two different types of bears. In general, your data will never be perfect. Even if the labels were manually produced by humans, they could make mistakes, like the Berlin team, or have differences of opinions on images that are harder to label, probably also like the Berlin team. Instead, we could replace all our ones with a number a bit less than 1 and our zeros a bit more than 0, and then train. This is called label smoothing. By encouraging your model to be less confident, label smoothing will make your training more robust, even if there is mislabeled data. The result will be a model that generalizes better. This is how label smoothing works in practice. We start with one hot encoded labels and replace all zeros with, do you want to?
Epsilon. Should I draw it?
Yeah, the third one.
Oh, okay. Why is it wasn't that bad, my epsilon. Come on, give me on first. Oh my god, it's just going further and further away.
Wow. How are you getting omega on that one?
It really is an epsilon. Don't be like that. Look, I get a yin yang.
Skull. That's when you know to end it. It's like, we're done.
Yeah, it's a skull. I wanted to make a skull. Let's keep going.
That's funny. Okay, replace all zeros with epsilon over n. That's the Greek letter epsilon, which is what we used in the paper that introduced label smoothing and used in the fast.ai code, where n is the number of classes and epsilon is a parameter, usually 0.1, which would mean we are 10% unsure of our labels. Okay. Since we want so it's always unsure, I guess, right? Like we're 90% unsure.
That's a lot. 90% unsure?
That's what, I mean, well, I don't know.
10% unsure. 90% sure.
If it's 0.1, that would make, it's interesting, right? Because like you would think that that's unsure, but saying 10% unsure means you're 90% sure.
I think so, yeah.
But 0.1 is pretty close to 0 if they're doing, you know what I mean?
Oh yeah, but it's not, I think that's just the value. Like it's not how close it is to 0. I don't think this is the same number.
That's what they were saying up top, no? Like replace all zeros. Okay. Then replace all zeros. Yeah, if you scroll up, it was saying things that are closer to 1, a bit less than 1, and 0 is a bit more than 0. Anyway, maybe I'm just like reading too much into it, or it was like a miswording. I don't know, right?
That this would actually be, it's 10% sure, like it.
That's what I'm thinking.
Yeah, 10% unsure. That makes sense. Like 0.1 means it's 10% unsure that it's a 0. like there's a 10% probability. That's probably wrong what I'm saying, but it's 10% unsure that it's actually a 0. And also when you have 0.9, it's 10% unsure that it's actually a 1. It always goes to the actual thing that it's trying to predict, and that's where the 10% comes in.
I understand that. I just think that maybe unsure should have been sure in this.
But it's not. It's 10% unsure that it's a 0.
10% unsure.
And with 0.9, it's 10% unsure that it's a 1.
10% unsure that it's a 0 because we're replacing.
Thanks, Chernovision. He's giving us.
No, I get that. I understand I understand how to, convert all of that. But
right.
By saying 10% unsure that it's a 0, you know what I mean? Because if it was 0.9, would you also use the word unsure? It's 90% unsure?
No, it's 10% unsure.
No, but if it was 0.9.
Right, then it's 10% unsure that it's a 1.
So you are just splitting it at 0.5?
No, because it's 0.1 missing to be a 1. So that's the 10% uncertainty.
But you know what I mean? I think so. You're splitting at 5, at 0.5. You're saying anything less than 0.5, you're using the word unsure. But then once it gets closer to 1, you're using the word sure.
No.
So, okay. So if this said 0.9, that would mean you are 90% unsure of the labels. Okay. No. So then you're changing the word unsure to sure.
No. I don't know. Let me try to see whether I can draw it up here. This beautiful thing.
Hold on.
And we can see what it predicts.
Hold on, because I forgot I can annotate your screen. Go back to that other.
Okay. Chernovision is 100% unsure what we're talking about.
I think I'm very close to that too.
I think I get it, but you want to draw. Otherwise, I could try to explain it. But I'm just going to eat my Krapfen.
Okay. I mean, hold on. I just got some PTSD from doing the annotations last time. How it was very messy. Okay. Using that highlighted within the parentheses.
I don't see anything on my screen.
I didn't
Maybe you
write
have to
anything.
save it.
No, I didn't write anything.
Okay.
I'm not going to because I remember it was messy last time.
Okay, so we're talking about this.
That line, right. So usually 0.1, which would mean we're 10% unsure of our labels. Okay. If that said 0.9, the only thing I'm changing, go into a text editor and literally copy that. Let me
try my drawing here. Look, so we have two possible predictions, right?
I feel like
we have 0 or 1. That's the two predictions. And we're saying we want it to be slightly unsure. So we're changing both of those a little. Instead of saying 0, which would be 100% accurate prediction, we're saying we're 10% unsure. So this is 10% away from what we actually want to predict. Okay?
Mm-hmm.
And the same thing on the other side. Here we're saying what we actually want is 1, but we're saying 0.9, which means we're 10% away from what we actually want to predict. And that's our 10% uncertainty. Do you see? Just 1 is up from 0.
Go back to the other one.
And the other one is down from, you know what I mean?
Go back to 10%. The second tab. I get what you're saying.
Mm-hmm.
It's less clear with the numbers that they used, I think. I think if they use 0.3, because then it would be 0.7 or something, that would be the opposite. Or if they give an example on the other end, like you're describing. I get what you mean. If they did the same thing with 0.9, they would say we're 10%,
unsure that
it's a 1. Yeah, that makes sense.
Yeah, I think that's what they're trying to say.
Yeah.
And I guess that's the point. You're like, I don't entirely get this, to be honest, but surprise. But I get that you want to introduce some sort of uncertainty so that the model doesn't.
No. I totally understand that. I think I was just hung up that.
No, I don't understand that.
Oh.
I mean, I think I understood that, but then the other, like, what's the whole point of making it unsure? I don't really get that. I think
that's that line where it says like the not good enough.
That means the
or
model
maybe
is
the model before the line up until that. So yeah, we could just reread it. Or one hot encoded to avoid during. Okay, we could put the same loss.
Means the model is trying to return 0 for all categories but 1. That's how we were doing it with one hot encoding, right?
Mm-hmm.
So the correct one, whatever, like it's correct one, the one that it thinks it is, it's going to be 1, and all the other ones, like we had this example up there, right?
Right.
So here, this, it thinks it's that, so it gives 1, and for everything else it gives 0. Even 0.999 is not good enough for the model. The model will get gradients and learn to predict activations with even higher. So it's just saying that when there's one hot encoded thingy, then it always goes towards, like, it always keeps going until it gets a 1.
Mm-hmm.
I guess. Yeah. So that it doesn't overfit.
Yeah.
Yeah. I mean, okay. If it's not perfectly labeled, because it's always going to try to go for an actual label. Mislabel different kinds of pairs. Yeah, I see. Okay, I think I get it. Okay, so we're here.
Okay, since we want the labels to add up to 1, replace the 1 by 1 minus epsilon plus epsilon over n. This way we don't encourage the model to predict something over confidently. In our ImageNet example, we have 10 classes. The targets become something like here for a target that corresponds to the index 3.
Mm-hmm.
Okay.
Yeah, those were all our planet dataset outputs were like that.
Mm-hmm.
Right. It's not a 0 or 1, but it's like a certain amount of what it thinks it is. And this essentially, I think these are probably 10 items.
No,
1,
I think
2, 3,
I think
4,
they're
5.
saying something different. This is what. This is not after the prediction. This is before. These are the labels.
And it spreads out the 0.1 over all of the things. The 0.1 uncertainty.
I don't think it's. I don't think they have to equal 1. Unless. Maybe they do, but I didn't understand that from what we read. It was just kind of like nudge it a bit above 0 and nudge it a bit below 1. You know, like if we had 100 of these labels, then I could imagine that it's still 0.01 on all of them and 0.91 on just the one that we're like, you think most confident of. I don't know. It's the same kind of thing. Like if
but here, like then you're thinking that's a coincidence that it exactly goes to the the missing 0.1% from 0.9 are just spread out perfectly across those 10 items with 0.01 each. It's a little suspicious that it's so perfect.
Yeah.
So it might be that if it's actually 100 labels, it would be 0.001 for each of them. Yeah.
It's kind of like that was the thing from the, like my misunderstanding above. Like it's not as clear that that's what that means. For me anyway, right? Like
yeah, I think it just says whatever you pick. Like that's the default is 0.1.
No, I know. It's like the 10% of it is like the 10% can go either way, right? Like for me to have understood this, it literally took you to draw out 0.9. What they're saying is just 10% the other way.
What is it actually? Idiot's int. idotsint. It thinks it's an idotsint, or it's the word.
I think it's a mobile phone.
Mobile phone. Or an Atari box. Mobile phone. Okay. Well,
From my understanding, they don't have to add up to 1. This is what softmax is, and they didn't say anywhere. Okay, yeah, I think that's my assumption too.
well, I don't know. I'm just saying. Is it a coincidence? It could be a coincidence.
So. I think they up
It's
until
just
now,
suspicious.
up until
That's all
now,
I'm saying.
they did a great job at explaining things further on, but I don't know who wrote this lesson.
They just dropping
dropping
it
the
to
ball
people.
on this one.
Yeah.
Introducing all these Greek letters.
Maybe it's in a
very-
sidebar though. You never know those sidebars. You know.
Oh man.
Here's how the reasoning behind label smoothing was explained in a paper by Christian Szegedy et al. This maximum is not achievable for finite zk, but is approached if zy is double error.
I think it's greater than greater than.
Greater than. I drew this. No, there you go. Guillemot, right? GG. GGG. Greater than? What's that mean?
I have no idea. You think it's greater than, but it's more than that. It's more than greater than.
Zk for all k does not equal y. That is, if the logit corresponding to the ground truth label is much great than all other logits. This, however, can cause 2 problems. First, it may result in overfitting. If the model learns to assign full probability to the ground truth label for each training example, it is not guaranteed to generalize. Okay, I get that. Second, it encourages the differences between the largest logit and all other logits and all others to become large. And this, combined with the bounded gradient dl divided by, that's some Greek letter, Nick, right?
Yeah, it is delta, but it's not. I don't know. The L is like
partial.
Oh, partial.
I don't know. Maybe not.
Partial. That's probably correct. It looks the same. Partial L, partial ZK.
Generation is saying they made the lesson optional for a reason.
That means much greater.
It is the ability to combined with the bounded gradient reduces the ability of the model to adapt. Intuitively, this happens because the model becomes too confident about its predictions. Let us practice our paper reading skills to try to interpret this. Okay, great. Thank you. This maximum is referring, this is so nice that maybe I'm gonna finally learn how to read some of these papers. Is referring to the previous part of the paragraph, which talked about the fact that 1 is the value of the label for the positive class. So it's not possible for any value except infinity to result in 1 after sigmoid or softmax. In the paper, you won't normally see any value written. Instead, it will get a symbol, which in this case is zk. This shorthand is helpful in the paper because it can be referred to again later and the reader will know what value is being discussed, if they do. Then it says, if zy bigger than zk for all k does not equal y. In this case, the paper immediately follows the math with an English description, which is handy because you can just read that. In the math, the y is referring to the target. Y is defined early in the paper. Sometimes it's hard to find where symbols are defined, but nearly all papers will define all their symbols somewhere. And zy is the activation corresponding to the target. So to get close to 1, this activation needs to be much higher than all the others for that prediction. So this means much higher.
Yeah, that's what Jonah Vision was saying is much greater.
Okay. Much greater.
Yeah, it's
much
greater than greater.
Also called much great in the here in the paper. I'm so picky. Next, consider the statement, if the model learns to assign full probability to the ground truth label for each training example, it is not guaranteed to generalize. This is saying that making zy really big means we'll need large weights and large activations throughout our model. Large weights lead to bumpy functions, or a small change in input results in a big change into predictions. This is really bad for generalization because it means just 1 pixel changing a bit could change our prediction entirely. Finally, we have it encourages the differences between the largest logit and all others to become large. And this, combined with the bounded gradient delta L or something divided by delta zk reduces the ability of the model to adapt. The gradient of cross entropy, remember, is basically output minus target. Both output and target are between 0 and 1, so the difference is between -1 and 1, which is why the paper says the gradient is bounded. It can be infinite. It can't be infinite. Okay, it's between -1 and 1. Therefore, our stochastic gradient descent steps are bounded too. Reduces the ability of the model to adapt means that it is hard for it to be updated in a transfer learning setting. This follows because the difference in loss due to incorrect predictions is unbounded, but we can only take a limited step each time.
Yeah. So Jonah Vision
thanks
said
for
a few
the training.
things. It's the partial derivative. L is a variable, and
partial derivative.
Yeah, and if I guess it seems like Tarzan.
L is a variable that's defined
much
somewhere.
Great.
Much great, right? So Tarzan wrote this paper. Much great. Okay, I thought this is. All right, cool.
Are you retaining any of this? Because I'm not.
Yeah, sure. I understand everything, and I also retain everything, always. Have you not noticed? My brain is much great.
All right,
much great perception. And sidebar. To use this in practice, we just have to change the loss function in our call to learner. To this, we're changing the loss function, where is it there, to a label smoothing cross entropy. Fun. Like with Mixup, you won't generally see significant improvements from label smoothing until you train more epochs. Try it yourself. We're still training something else. Try it yourself and see how many epochs do you have to train before label smoothing shows an improvement. Okay. Conclusion. Nick.
Sure.
Bring it home.
In conclusion, so you've now seen everything you need to train state-of-the-art model in computer vision, whether from scratch or using transfer learning. Now all you have to do is experiment on your own problems. See if training longer with Mixup and/or label smoothing avoids overfitting and gives you better results. Try progressive resizing and test time augmentation. Most importantly, remember that if your data set is big, there's no point prototyping on the whole thing. Find a small subset that is representative of the whole, like we did with ImageNet, and experiment on it. In the next 3 chapters, we will look at other applications directly supported by fast.ai, collaborative filtering, tabular modeling, and working with text.
Yay.
Yep. We will go back into computer vision in the next section of the book with a deep dive into convolutional neural networks in suspense, open and close brackets.
Cool. Yeah, true. So that was the whole ImageNet point that we glossed over in our beginning recap, that the point of making this ImageNet was that you can get a representative sample of a larger data set. And if you do training on that, you get relatively good results, like representative results for the whole thing.
Yep.
Yes.
So with this, it's there's no point prototyping on the whole thing. So ImageNet seems like it's a prototyping method, right? Like
correct.
You take this, and then eventually train on the whole thing.
Mm-hmm.
So what do you want to do?
Like you can use the small ImageNet to develop to develop models that work well on the big ImageNet too. Yeah.
So what do you want to do in the next stream? You want to train with Mixup? I mean, it said like greater than 80 epochs. Yeah, I don't know that we have time to do that.
No, we keep going, Nick. Let's keep going. Let's keep going through the course, and then.
Was this not the optional section that you wanted to do? Yeah.
Yes, absolutely.
So you don't want to work on this at all.
It's a little inconsistent of me, huh?
Well, yeah, because I mean, we learned this now, or we read it now, and now we have to apply it on something.
We will, of course, we will apply it when.
No, we won't. We
will once our brains have been enlightened by going through the full course and going all the paths and annoyances of working on stuff that slowly brings you knowledge. No,
I don't think.
Isn't that's not how it works?
I don't think so.
I thought that's how it works. That's how I usually learn stuff.
I don't know.
No. Okay, well, I gotta go pack. because I need
Go
to go
pack.
to bed so I can get up early tomorrow.
Go pack. We'll chat with all this stuff. Best of luck tomorrow.
Thank you.
And
So wait, recap. What did we learn? Test time augmentation.
we learned what Mixup was.
So test time augmentation was okay, so this issue that if you have multiple labels, like you don't want to crop out something that might be important for the image. So what you can do instead is creating multiple versions of each image using data augmentation and then taking an average of the predictions. Like you predict for all augmented versions and take the average of all of those predictions. That's test time augmentation. Mixup, we said, okay, combine, what the fuck was that? Excuse my language. Then you combine two images, like one that you're interested in and a random one, and make a new image. And then, okay, I don't have the head for this today.
I thought you retained everything, always, Tarzan.
Yeah, I just don't have the head to explain it to you, Nick, because you're so slow in understanding all of that.
Could you go to the third tab really quick?
What's that? This one?
No, the third one.
Oh.
And then can you just draw out the explanation so that we can all understand?
Okay, yeah, okay. It's like that. Yeah. It's clearly a phi.
It really doesn't.
Well, if you squint, then it kind of looks like this.
Oh, man.
Okay.
Anyway, yeah, I think we learned stuff that we're not going to use clearly.
So, John Visions, you want to join next?
If
yeah, sure.
You guys do the next
Hop
lesson.
on. Explain us everything. Next lesson. You did it probably already, right? Lesson 8. You can. Okay,
yeah,
so
are
next.
you on lesson 8? Are you on this?
Okay, I like that.
Was it?
John Vision, next
filtering?
stream, you're gonna walk us over lesson 8. We got a deal here. Nick and I, we're gonna make sure that we're as little prepared as possible, so that it's that you have a green field in front of you.
Yeah. Less prepared
Fertile
than
soil.
we usually are. So do with that information as you will.
Nice. Okay, I like it. You got the link. Thursday. If things go well, I will be in this same room.
Best of luck.
Thank you. All right, that's all. Logging off. Have a nice day, everyone.
All right, see everybody on Thursday.